Let's remember the setup we have for this problem. We have a recent article states that 98% of people who travel on the New Jersey Turnpike exceed the 60-mile-per-hour speed limit. Law enforcement officials are planning to covertly measure the speed of 750 cars on the turnpike and will compute the proportion of drivers who exceed the posted speed limit. And remember, we determined already that it should be normally distributed with a center of 0.98 and the spread of 0.005112. Okay, so we already found a probability. Now let's find a percentile. So what is the 37th percentile for the sample proportion of drivers speeding? Okay, so we need to make a picture of that. It's going to be on the low side, and I changed this from 87 to 37 in the original notes, so make sure you make it 37. All right, let me go draw a picture. I'll be right back. All right, there we have the picture. So you can see I'm on the bottom side because I'm at the 37th percentile. That area that we've shaded right there is the 37th percent. And what we're asking is, what is this p hat? What is that vertical line running down the middle of the graph? All right, so, and again, let me look at the decision matrix. I'm looking for a percentile. I want to find a percentile, so I'm going to be using inverse norm. And again, I'll put those in the notes. So I want to use inverse norm. And if you're watching it in the fall of 2014, I'll put them, I sent them via email to students. All right, so inverse norm, 0.37, and then 0.98 was my middle term, my mean, the center, and then my standard error, not standard deviation, but standard error, is that big square root. And again, it's a little bit more accurate to use the big square root than it is to use rounding, although if you round to 6 decimal places, you'll be close enough. So let me clear all this out. Second distribution, number 3 now, inverse norm, 0.37, 0.98, and I'm going to use the big square root because I like it. 0.98 times 0.02 divided by 750. Now I got a little crafty in there because I know that 1 minus 0.98, if you remember the formula, I know this part is the complement of this part. So if I know this is 0.98, then I know this is 0.02. That way they make 1. So now if you like, you could put parentheses in there and put 1 minus 0.98. That's fine as well. But I just wanted to show you could do it another way. And then press enter and then enter. And you get 0.9783. Okay, so let me go put that in our answers. So p hat, let me type it up 1 second. There we go. P hat is 0.9783 or about 97.83%. All right, let's move on to the next one. So still got a random sample of 750 drivers. What is the probability that less than 728 of them are speeding? All right, well, you're going to have a little bit of an issue because this is a p hat down here. This whole axis is a p hat axis, right? So proportions. 728 is not a proportion, so let's make a note of that. 728 is not a proportion, so we have to make it one. Using the formula, make it 1. Now there's a formula for p hat that we saw way back at the beginning, right there. P hat is x over n. All right. So, oops, I'm running out of space. There we go. Okay, p hat is x over n, which is, in this case, 728 over 750 because n was 750. Now you could find what a decimal approximation for that is, but it's not going to be great because I believe this one goes on forever. 728 over 750 is 0.9706 repeating. 9706 repeating. There, 9706 with the 6 repeating. All right, now that's what we'll use. So, and you can see I already drew it right there on that. So the p hat is 0.9706 with the 6 repeating. All right, now we want to find, now think, we're looking for a probability. Probability, let me bring back that decision matrix that I'm going to put at the end. If you want a probability, you're going to be using normal CDF. So let me type that up. Normal CDF from -1 E99 all the way up to, now honestly, you're better off using the fraction here. Because it's a repeating decimal like that, if you start rounding, you're going to lose accuracy. So keep the full fraction, 728 over 750, then 0.98 for your mean, your center, and then for your standard deviation, I would recommend using the big square root. And again, if you want to round, that's fine, but then you're going to have to use at least 6 decimal places. There we go, I got that all to fit. All right, so I've got that now. Okay, so now that that's in there, then I can go find that with my calculator. So let me clear this out. Distribution, I want number 2, normal CDF, from -1E99 all the way up to, and I want to type 728 divided by 750. I mean, why bother with a rounded decimal when you can have the calculator figure everything out for you? Then I'm going to use the square root, 0.98 times, and again, you could either use 1 minus 0.98, close your parentheses, or you can just type 0.02, and then you would divide by 750 for both of them. I think it's just a little bit easier to do this way, but if you want the parentheses 1 minus 0.98, knock yourself out, right? You'll be fine. And you get 0.0339. There, I typed it in. All right, would finding less than 728 of them be unusual? Well, yeah. I mean, unusual for our purposes up to this point has been anything less than 5%. And 0.0339 is less than 5%, so that would be unusual. So then, suppose it happens. Suppose you go out there with your radar gun, you're a policeman, you go out there with the radar gun, or policewoman, and you get 750 cars covertly, and you get less than 728 of them speeding. What conclusions might you draw? Well, the kind of obvious ones are maybe it's a biased sample. And these are the 3 broad ones, but you have to explain each one. So perhaps they can see the car. So it's not as covert as you thought it was, not as covert as you thought. Perhaps you're not any good with the radar gun. Perhaps you just, perhaps you are not good with the radar gun. Or the radar gun is broken. Perhaps the radar gun is broken. Now, let me make this a bulleted list. I don't like all these perhapses. 1 second. There we go, we got them in there. So these are some possible ways this could happen. Then perhaps it's just a fluke, just by random chance. We had a slow group. Now the probability of this is 0.339, what you found already. So pretty low. That leads to one other thing. If you say, look, I didn't have a bias sample, my radar gun was fine, right? And it wasn't a fluke. I think that's too low for it to be a fluke. I think something else is going on. This smells fishy, right? Well, what could possibly else be wrong? The P equals 0.98 is from the article is not correct, right? In other words, we built everything off of that proportion, that population proportion we believed to be the case. We thought it was 0.98, but what if it's not? Or what if it was and is no longer true, right? This is how you start proving that things are changing. So let me make a note. This last part, parameters wrong, is what we work with in chapters 9 and beyond. This is how you start making arguments that things have changed, values are different, someone is lying, etc. This is how you start doing it. by saying, look, I think the fluke is out, I think the bias sample is out. And if those two things are not an option, that leaves you only one other option, and that is parameters are wrong, right? So you would have to explain each one of these three, say on a note sheet or on your exam or on a worksheet, that kind of thing, or in a project. But those are the three options. And this last one in particular is what we start working with in chapters 9 and beyond. All right, we're all done with chapter 8. I'll see you back here for chapter 9, which is when we start making those first leaps into inferential statistics. We'll be working with confidence intervals. See you then.